Hi everybody, Professor Burns here. I want to start chapter 6, and in this chapter we're going to look at a probability distribution and a couple different ones that are kind of big and kind of central in the study of statistics. But first I just want to get into what is a probability distribution. So make sure your cell phone is put away and you have your notes out and you're ready to listen carefully. A probability distribution is essentially a way to display different probabilities for different events. It tells us two key features. So the first is all possible outcomes for an event. Okay, so all the things that could happen. And then it tells us the probability for each of those outcomes. So the probability for each outcome. It could be displayed as a table. It could also be displayed as a graph, and it depends on the type of variable that we're looking at, which we'll get more into in just a moment. Two key characteristics that we need to keep in mind. All probability values, remember, just like back in chapter 5, probabilities have to be between 0 and 1, right? So everything, all of those individual probabilities have to be between 0 and 1. And of course, the sum of all of those probability values, if we're considering all the outcomes in an event, must total up to 1. Consider the random variable x such that x is the outcome rolling a die. So we're going to look at the situation where we're rolling a die, and we want to create the probability distribution for this random variable. This is what we call a discrete variable because there's 6 outcomes that we can count. 1, 2, 3, 4, 5, or 6. There's no in between. It's just those 6 different outcomes. So I'm going to use a table to set this up. And I'm going to do 2 rows here. I'm going to call the first x, where x is each outcome, and then the second row is the probability for x. So what are my different outcomes? X could be a 1, a 2, 3, 4, 5, or 6. And then what is the probability for rolling a 1? That would be 1 out of 6. Probability of rolling a 2 would be 1 out of 6. 3 would be 1 out of 6. 4 would be 1 out of 6 because they're all equal in this case. 5 would be 1 out of 6. And again, I'm assuming this is a fair die. And 6 would be 1 out of 6. So a couple things I want you to notice. Each of those probabilities adds up, or each one is between 0 and 1. They're all the same. They're all 1/6. And if you add all those together, the total would be 1. And that's because I've considered all possible events for rolling a 6-sided die. What is the probability of rolling a 5 or a 6? Those are mutually exclusive events. So the probability of rolling a 5 or a 6, I can simply add up those two individual probabilities and I get 2 out of 6, or of course 1/3 if you want to reduce it. Now let's talk a little bit more about the two types of variables that we work with. Numerical variables that you can count or number, I guess, maybe what I was looking for here. So like what we had here, I've got 6 different variables. It's a 1, 2, 3, 4, 5, 6, or not variables, 6 different values that were possible. That's called a discrete variable. There's no in between. There's no 2.5. There's no 3.5. So if I can count the outcomes, that's discrete. Variables that cannot be counted because they occur over a range of variables, those are called continuous. And usually those are going to involve some sort of measurement, weights, heights, things like that. Those are going to be continuous variables. So let's do a little practice here and talk about the difference between discrete and continuous. First is the number of siblings that somebody has. Well, do you count or do you measure siblings? You count the number of siblings, so that would be discrete. The heights of basketball players. Well, we measure heights, so that would be continuous. Number of cars owned by a household, we count that, so that would be discrete. Number of pets owned, again, that's countable, so that would be discrete. Heights of buildings in San Francisco. Heights are something we'd measure, so that would be continuous. Wait times in a doctor's office, we'd measure times, so that would be continuous. And I just realized something in my notes. I'll see if I can fix this in yours. I spelled weight wrong. This is the weight, like your weight. How much do you weigh? I meant wait times. I think I should have used W-A-I-T. So if you need to fix that in your notes, go ahead and do that. But either way, it's a time that I'm interested in. So times are something we measure. So that would be continuous. It would be over a range of values. I could be waiting in the office anywhere between 5 and 10 minutes and anything in between. Since the values of a continuous variable cannot be listed, so this is really the key difference here. If it's a continuous variable, we can't list them the way we did in this table. So when it's a continuous variable, we have to use some other way to display the data or display the probabilities. A probability distribution that uses a table or what's called a spike graph. I think I have an example of that in the notes or in the exercises. But either way, a table is more useful for a discrete variable. This sentence is worded a little bit awkwardly. Let me see if I can clarify this a little bit. Continuous variables we're going to display on a graph. Whereas if it's a discrete variable, we'll use a table to do the display for the probability distribution. When it's continuous and we're using a graph, the name of it changes slightly to a probability, to a density curve or probability density function. You don't have to remember that term directly, but what you do need to remember is that if you see a graph like this, this means you are using a continuous variable. This would be a measurement of some kind. All of the heights for a certain breed of dogs, all of the weights for a certain type of animal or whatever. These graphs have an area under the curve that must equal 1. So whereas with a discrete variable, the sum of each of these probabilities has to total up to 1, but with a continuous variable, the entire area would have to total up to 1, and that's the idea. The area under the curve represents a specific probability. So in this little picture here, what they're saying is the area that's shaded in purple is the probability that the variable is greater than or equal to, because it's shading to the right, this x sub 1, whatever that is, and I'm not sure. This looks like it goes with maybe a bell-shaped or a normal distribution curve, which we'll talk more about in the next section. But what I want you to remember from this lesson are a couple of things. The difference between discrete and continuous variables, that's very important. And the fact that when we have a discrete variable to display the probability distribution, we're going to use a table, and each probability has to add up to 1. But when we have a continuous variable, we're going to use this density curve, and the area that's shaded represents different probabilities. The total area under the curve has to equal 1. And we'll look at some practice with this in class tomorrow, so bring your notes with you, and I'll see you then.